the past years, and typically telling one or the other to different communities. Hopefully that will be appreciated, and if you don't, that's okay. I don't mind, but I think it's fun to think along new directions. Many ways, so you will see. First of all, I need to thank many of the collaborators. This is just a very, very short and over. It's okay, I'm using your pictures, so please tell me if it's not okay later. But I have to say, I learned immense amount of physics from all these collaborators, and there are many more from which I learned from, but I took a selected class that is related to what I'm gonna talk about today from the first part of the talk, which is about energy physics. This is the list of the papers on which this talk is based. I'm not pretending you to go through it, but if this is available later, you can actually go and look at the references. Okay. So let me start from the Standard Model. As you know, I'm a particle physicist, and the Standard Model is kind of ingrained in my DNA. So this is the skeleton of the Standard Model for particle interactions. What do we know about it? Well, the gauge part is extremely well tested. Okay, so there is no doubt that the gauge part is correct. This, I mean, the SU3 cross SU2 cross U1 of the Standard Model. The Yukawa sector, it's what is responsible for the entire flavor program of the Large Hadron Collider. And as you know, this is very exciting because there are emerging anomalies that might lead to a breakthrough and the need to go beyond the Standard Model. Then we have the Standard Model self-coupling, which has not been measured yet. And it is this goal of the future colliders to pin it down. It should be very clear that unless you measure this very clearly, we cannot say that this is the Higgs of the Standard Model. Okay, so it's an important thing to keep in mind. And then there are two more parameters. Let me just go to the next slide, which deserve a little bit of attention because they have led and most of the interest in particle physics and even in cosmology for the past decades, because both are related to, in our jargon, super-normalizable operators. And as you know, they actually typically lead without supersimilar, without any other protections, to additive renormalization. And therefore, they meant to be not stable against quantum corrections, also known as technical naturality or the cosmological constant problem. But in practice, they have origin in both in the fact that they are super-normalizable operators. And they are the only two indeed that are non-marginal at the classical level. So this is a nutshell summary of the status of the art for the Standard Model particle physics. Very brutal, okay, very brutal. But it is a fact, sorry. It is a fact that it is actually a gauge theory, a quantum field theory. If we, for example, focus on QED, we also know that QED is an effective field theory. So if we now just zoom in the QED part of the Standard Model, we know the QED is a Landau pole. You could hope that high-order corrections will fix it. And in fact, you can show this related to a work I done with Oleg Antipin, that, you know, if, for example, you consider the leading NF corrections to the running of the coupling constant, this Landau pole does not go away. This is not a proof. So full proof that the Landau pole is there, but clear that the leading of the NF it's there. But we also know there are parts of the Standard Model which are well defined in ultraviolet, right? For example, QCD is a famous example of that. There is no UV cutoff in QCD because actually the theory, as you can see here, the theory has a perturbative ultraviolet fixed point, or known as trivial UV conformality. On the other hand, it gets very interesting at low energy, right? It gets strongly coupled, and this is not a Landau pole, but it interpreted as by dimensional transmutation into the emergence of a new scale, right? Often identified with a confining scale, but in QCD there is no confinement because there is no order parameter for that, but it's definitely chiral-symmetry break. And this is the region where lattice QCD has been exploited to actually determine the spectrum of QCD. And it works extremely well. In fact, the lattice QCD through the alpha collaboration was even able to determine the running of the coupling constant via the Schrödinger function to high accuracy. So this is a good theory. You can generalize the idea of asymptotic freedom to theory with scalars. For example, in gauge-Yukawa theories, you can have, and this is in the Yukawa gauge coupling, you can have that the same gauge-Yukawa theory can at the same time be either completely asymptotically free or actually have a Landau pole in the Yukawa. The green line here separates these two phases. So in other words, a gauge-Yukawa theory can simultaneously be an effective field theory or a fundamental field theory according to the Weinberg and also the Wilson idea. So it actually can be a fundamental field theory or both a effective field theory, and very much it depends on where do you start in your renormalization flow. So this is if you want given by the low energy data. Very good. So I will not go through. We studied this analysis in terms of many other limits, and we have this under control because it can be done in a perturbative manner. A little bit more interesting is what happens if you assume that rather than have a trivial ultraviolet fixed point, you have an interacting one. And this has eluded us for several decades. In fact, according to David Gross, he was searching for these theories because he was afraid that asymptotic freedom were not actually the only theory that could be fundamentally at short distances, but they failed. And the reason on their failures was that they did not start, first of all, they did not have all the tools that they should have in the 80s. And secondly, they did not study theories with Yukawa couplings. So you can actually ask whether you can have an ultraviolet field theory that it is interacting. So basically, this is actually possible to imagine to have that. And the first rigorous proof actually happened with the discovery with Daniel, that in fact, a very simple theory that is a QCD-like theory with the scalars which are not gauged, but have Yukawa interactions, can have an interacting fixed point in ultraviolet. And this is can be proven rigorously by going into the Veneziano limit. In the Veneziano limit, you can consider the different four couplings scaled by the different corrections in the number of colors and flavors. And you can define an epsilon parameters, which is not the epsilon we're going to discuss later as the deviation from 4 dimensions, but it's an epsilon parameters in the term of a Ben-Sachs that you can consider as a deviation from a number of flavors or divided by number of colors from the loss of asymptotic freedom. This theory, I will not go through all the proof, but this theory indeed has an ultraviolet interacting fixed point. And this corrects the famous paper by Caswell, and there was a student of David, that in '74, that they say that he was searching for ultraviolet fixed point with theories with fermions, and he couldn't find them in perturbation theory. And then he made this very naive theoretical physicist mistake to say, well, you can't in perturbation theory do it with the fermions, and I expect the same to be true also with scalars. Clearly, you have to prove things. You cannot just mention it. So this is a counter-proof of that. And this is actually the scaling. These are the scaling exponents of the ultraviolet fixed point. And you can see that this fixed point is attractive from some of the Yukawa directions, and is repulsive as it should be from the gauge directions. Of course, I cannot visualize for you the fixed point with respect to 4 couplings, because it's still with the 4 couplings. So the best I can do is to visualize it in 3 dimensions. This is not a cartoon of a fixed point. It is actually the fixed point, right? So this is a natural fixed point. And this is a natural running of the coupling constants. So again, it's not a cartoon. This is the solution of the theory from that point of view. And you see the gauge coupling, in that case to the safe fixed point, the Yukawa coupling, and then you have the single trace and double trace operators, The double trace is negative, the single trace is positive, but the sum is actually positive. Sorry, it's negative, but the sum is positive, which means that you have a very well-defined column. So there is no effect of the Coleman-Meinberg. Just a second, I need to say something to my. All right. So lambda here, on the other hand, it's a transmutation scale that separates the two sides of this fixed point. If you want, if I go here, lambda roughly separates the basin of attraction of the ultraviolet fixed point from the infrared one. And it is a renormalization group invariant scale. So this object is a physical quantity. Very good. So where I want you to go with this is that the CFTs allow you to define the ultraviolet and infrared properties of the theory. And in the case of the ultraviolet, what we will consider fundamental from the point of view of Wilson and Weinberg. Now, if you have a fixed point in the ultraviolet with all repulsive lines, this can go in infrared anywhere. So this is a theory which is infrared unpredictive. There's been a huge, not misunderstanding, but let's say, some colleagues were searching for this type of fixed point as a theory which is stable in all directions in ultraviolet, but you missed the point that this theory is unpredictable in infrared. It can go anywhere. Of course, you always get to the ultraviolet fixed point, but there's no prediction in infrared. If, on the other hand, you have a theory which is stable in only one direction, I mean, track only in one direction, then this actually leads to a unique infrared physics. And then, of course, that predictive in infrared. Of course, I'm not saying that this is the only way to do that. You could also have other possibility, but this is certainly a very predictive in infrared. All in behold, CFTs can be seen as lampposts for defining a theory of fundamental interactions. So this means that you could actually have a very well-defined theory in ultraviolet. And this is a slide that summarizes exactly this point. So fundamental theories, theories which have ultraviolet fixed points, either trivial like asymptotic freedom, or interacting, or a combination of both. This is from the QFT point of view before adding gravity, but you can, from the phenomenological point of view, you can say, well, but we still have to add gravity to this, so this will presumably change the ultraviolet property of the theory, and that is actually true. So the question is, how do we go beyond that? Well, if you consider the standard model, this is the energy scale, or the renormalization group scale, if you want, and this is a generalized alpha of the standard model, then we know the physics here. Between the electroweak scale and the Planck scale, you might have some new physics that might change the running of your coupling, maybe by making it safe or fully asymptotically free, or a combination of both for the various couplings. And the question is, what happened at the transition with gravity? An example could be R-squared gravity, right? In this case, the theory is renormalizable, but it has a problem in the sense of causality or microcausality. It's violated because the theory has ghosts. But this is a theory for which you can calculate everything. And in this case, there is nothing happening here. So you can actually believe to your quantum field theory computations. What is the trick here? The point is that R-squared is asymptotically free on its own. So if you go toward the ultraviolet, it will not affect the other couplings. So that's the way it is. The other program you could follow is the Swampland program that Aaron heralded together with other colleagues. And it's an interesting program that recently I've been investigating out of my research curiosity. And it more or less, doesn't look like that, but that's what Swampland really looks like in real life. But it's more like this, okay? So, and Aaron can correct me at any point if I see something which is not correct, okay? So now you have some quantum field theory at low energy, whatever it is, and then you have some quantum gravity at some very high energy. eventually you need to connect these two. So you can think about sewing together two different stuff, and the things have to patch with each other. If they patch, they define for you a dry land. So these are the set of effective field theory consistent with the quantum gravity. If they don't belong to the dry land, they remain into the swampland. So the program could equally have been called dry land rather than swampland. I guess it depends whether you look at which part of the effective field theory you look at. Okay. So this is a nutshell, basically the idea. But how do you go about that, right? So driven by string theory, mostly string theory, a number of conjectures are employed to try to select the different effective field theories. Okay, and bear with me, I will just make a laundry list of them, right? I studied them, but Aaron certainly knows more than I do. The first one is a very, very, very old conjecture. It's about an global symmetry conjecture. It tells you there are no global symmetry in nature. This is a very powerful predictions, right? Because if you go to the standard model and you see the famous B minus L, which is an accidental symmetry of the standard model, according to this no global symmetry conjecture, it either should be broken or should be gauged at some higher energy. Now, the question is that, unfortunately, the no global symmetry conjecture doesn't tell you at which scale, I mean, how small is broken. So, in fact, it will be very, very tinily broken, so it's very hard to test in practice. But this is actually the moral of the no global symmetry conjecture. Now, you can generalize this no global symmetry into the completeness conjecture, right? And that can be, the statement for that is below here. So theories featuring a gauge symmetry coupled to quantum gravity must exhibit all states of all charges, of all possible charges. So this is another prediction that comes into place. In string theory, the no global symmetry conjecture is kind of trivial in the sense that any global symmetry is always, in the darkest space, is always gauged on the worldsheet. So effectively, no global symmetry is for free. Then there is another conjecture that comes from mostly from string theory. It's like when you compactify some extra dimensions, there are moduli, and you can actually argue that there will be always an infinite set of states that, with respect to another set of states, will become infinitely light. If you want to have something in your mind that to fix your ideas, you should think about, if you have string theory, you have both Kaluza-Klein, but also winding modes. And they're anti-correlated when it comes to some internal bulk radius, which can be seen as a modulus of some field. Finally, you have a species scale conjecture, which has to do with the fact you have many, many copies. This has been used a lot in particle physics when we were studying extra dimensions. Because then you have many copies of the same particle, so that for you effectively defines a cutoff and a physical cutoff that tells you that theory is valid up to that cutoff. Another interesting conjecture, which is the weak gravity conjecture, which in a nutshell means that gravity is the weakest force. So if you think naively about the fact that you can make bound states in quantum field theory, take QED, then this you see that the bound states should actually be typically the interactions are proportional to the coupling square times the charge square. This should be larger than in what you can get by having gravitational bound states, which is m squared over m squared Planck, and effectively you can then rewrite this as m less than some number times the coupling constant, the charge, and then Planck. Now, I don't want to get into all the problems that this actually can give you. I mean, what kind of scheme you're computing this and so forth, on, because it's very vague written at that, and this number depends on the specific model of quantum gravity you're going to have, right? So all these conjectures have the problem that either they're string theory dictated, so not necessarily apply to any quantum gravity, or a little bit too hand waving. And Aaron has, in his review, has made it very clear many times about where the hand waving were coming about. But I was extremely pleased to see the paper by Ofer and Aaron, because they provide a very sharp version of the weak gravity conjecture, basically based on the idea of bound states, right, in the bulk, where in saying d+1 dimensions, that you can get when you have gravity and say quantum electrodynamics. And if you think about the idea as CFT, you can imagine that what was a gauge theory in the bulk becomes basically a global symmetry in the on the boundary. Then the masses of these bound states are naively can be mapped into the conformal dimensions on the boundary, and then the convexity or super addition properties that if you actually calculate the anomalous dimension or the conformal weight of the sum of two charges, that should be larger equal that the conformal dimension of each of the two, okay? So as I said before, the physical interpretation of positive binding energy, I'm sure that Aaron is going to go through that in extremely excruciating detail. But to me, for the non-abelian case, immediately came to mind the Mach. I don't know, I'm probably old enough to remember that. But in the 80s, to see whether you had the possibility to have attraction in different channels for a single gluon exchange, in which representation you would have that, you would look at the famous most attractive channel. And the most attractive channel is always a fully antisymmetric channel. The symmetric ones are always actually non-attractive or typically not attractive. And we want for this inequality to hold, indeed, the non-attractive channels. So the symmetric representation are the natural candidate for non-attractive channels, because effectively that was the naive expectations, which was confirmed from one gluon exchange a long time ago. It has to do with the group structure of the theory. So I have to say, this is something that I don't think it was in the paper by Hofer and Aaron, but it did remind me of that. And one can discuss that, whether it's usable or not. All of this to say that we need to solve quantum field theories, because, for example, in this, according to this conjecture, at the end of the day, you look at conformal dimensions of operators of charge Q, where gravity plays no role at all, right? So how do you actually go about to solve a quantum field theory? This is a little landscape of possibilities. And of course, we're interested in principle, even in strongly coupled theories, but that's even harder than just perturbative one. So you can apply perturbation theory. You can use lattice, you can use bootstrap, you can use a Fetty description, you can take 1/n, 1/nf, 1/q, holography, SUSY properties, semi-classical approximation, resurgence, higher spin, you name it, but or a combination of all of those. And in fact, in several of our papers, we have used a combination of all of these approaches. Each single methodology has its own limitations. For example, if you consider perturbation theory, you know that you have to stop to the order alpha to 1/alpha. If you take QCD, this alpha to 1/alpha is pretty close. That's why it makes a little sense to go to 7, 8 loops in QCD, because alpha being 0.2, it doesn't really help to go to very high in perturbation theory, and you can stop to the first few ones. If you have multiple couplings and you do perturbation theory, then, for example, you have to take into account the wild consistency conditions to order the running of couplings. In any case, in perturbation theory, after a while, Feynman diagrams become cumbersome, right? I mean, for example, our colleagues Jack and Jones have been doing an amazing job there, and they keep doing it. And thank God they're doing it, because we're using very much their work too, constantly. So one would like to go beyond that. So let me take one example for that, okay? So I will not bore you with many, many examples, and I just decided to take one of that. I will not review the large charge, computations. So for some that were actually extremely well reviewed on Monday, but I just considered this. So let's take the model chart that's been cited by different people. And we know that in Feynman's epsilon dimension, there's a fixed point. The action is trivially written like that since the dawn of particle physics, effectively. And this is the one loop, fixed points, the infrared fixed point. And now, as Domenico, Susanne, and many others did also earlier, you can just fix enough charges because it's the rank of n. I'm choosing n to be even. And little aside, for epsilon equal to 0 and n equal to 4, this is the standard model X. Okay. And then for different epsilon, for sub epsilon going to 1, you have magnets, superfluids, helium 4, and so forth, so on. So what can we do here? Okay. Let me just consider operators with the minimal scaling dimensions. This is exactly the kind of operators that Ofer and Eran were interested in, because again, these are the one that a good chance that gives repulsive binding energy, and that is, I would say, what remind me of this Mach principle. And then you can consider the sum of the charges, and if you consider different operators, for example, single operator will have charge 1, the totally symmetric operator will have charge 2, and so forth, so on. You can also interpret these operators as the introduction of anisotropic perturbation in the theory. And the conformal dimension become the study the stability of the system versus anisotropic perturbations. So as we were taught, you can actually determine the ground state energy here. You obviously using the state operator correspondence in this. And you can see that I can define these charges. I can rotate it in a single charge, and then try to calculate the partition functions between two fixed charge states. Once you introduce the sigma coordinates, they will acquire a VAV, and chi will be related to the chemical potential, which is the Lagrange multiplier for the charge. At this point, your effective action has 3 terms. So the original effective actions, the term that fixes the charge, and echo-formal coupling, okay? Because we are actually a non-trivial manifold. R is the radius of the cylinder, and D is the dimension of the space. All right, so what we would like to calculate is this conformal dimension here, expanded in 1/Q, where A is G times Q, okay? And this is gonna kept fixed. So if you want to calculate the first term that starts with k equal to -1, then you look at the classical part of the action. This is what you do in any kind of subtle expansion. And you can write it in closed form. And X as this term here. And this already resembles an infinite class of diagrams. This is the original operator that you have there. And then it's lambda, basically, the fixed point. And then you can see all the different would be loops you have to calculate to already look at the first part of this function. Delta 0 is a bit trickier. I mean, because you have to calculate the fluctuations. So you have to solve for the determinant of the fluctuations around the background. And this as this expression, where R is still the radius, L labels the momentum eigenvalues with the degeneracy NL. And these W's are nothing but the dispersion relations of the different particles in the system. Of course, you broken Lorentz invariance because you are a fixed charge, if you want the chemical potential. And this W plus minus W plus and minus, this corresponds to relativistic particle with charge with mass 6 mu. 0 means relativistic. This is the photon, and this is this, or the conformal mode. This is actually the speed, light speed in, or sound speed in that medium. And then you also have some non-relativistic states that you could interpret as magnets. You include all of them, and you can derive the formal dimension of this operator Q. In closed form, for delta -1, you have it analytically. For delta naught, you have it numerically. Now you can re-expand in terms of small toothed coupling. Remember that this is little a is GQ, okay? So that's fixed, but you can take it small, and you can re-expand it. And this gives you, once you do that, this gives you this to compare with perturbation theory. Now, if you combine it with the knowledge of the full loop, for loop calculation for Q equal to 1, 2, and 4, we could reconstruct an entire for loop calculation too. And this, I would say, is the state of the art currently on the ON for minus epsilon there. The red parts are the ones coming from the delta minus 1, the leading term, and the blue parts are the coming from delta naught. It contains an infinite number of checks for diagrammatic computations, and that's what actually Ian Jack and Janks have actually checked too, recovering these results. Of course, this has been done by several of you, like Domenico, like Susanna, in lower dimensions of Rason, but I think if for myself, will be pushing very hard on that. If you now go to the 4 dimensions and epsilon equal to 0, you can turn the CFT in computation into computation of an anomalous dimension of the charge operator, and this is the corresponding perturbative corrections up to order g to the cube. So you can smoothly go from the CFT to the QFT, which is okay, it can be done. It's interesting. Which is, for example, interesting because this is, for example, related to the Higgs of the standard model. Okay. So excellent. So I'm going to present now work in progress. That's something that we've been inspired by the work also inspired by the work of Ofer and Aaron. So we actually said, okay, what else can we learn from the computation we've done? And I know Jiwei is there, and he has been actually working very hard on this. So how do we relate to the work of Aaron and Ofer? Well, in their work, the charge Q is actually N. And this is again of the ON form epsilon test that they were doing. And then they define a quantity which is basically delta phi of the operator phi n1 plus n2 minus delta of n1 minus delta of n2. And they checked in perturbation theory that this was actually positive. Now, technically, they were really doing perturbation theory. So we're doing, if you look at our expression here, you take little q to be n, I don't think I've written here the expression, right? But effectively, that's what they've done. They go to the small, effectively charge a small n in order to be able to do that. But in truth, we know the full first term and the second full first term. So one thing fun that we wanted to do, it was to say, okay, in order to prove this for a single for function or a single coupling is enough to prove the convexity of each delta. Okay. So let's see what are the convexity properties of each of these two functions. So interestingly, at least we found interesting, and this can be generalized. Since you want to look at the convexity, it's enough to study the second derivative of the function as a function of n for delta minus 1. This is always positive for arbitrary n. And you can also consider the second derivative of the sum. In fact, you also know that delta 0 itself is actually also convex, and the sum is convex. So the convexity applies much more strongly than just to the perturbative result, but it's actually for the two functions independently. It didn't have to be like this, right? It could have been just the sum. The moment is just an observation. We have more interesting results that I'm not going to present now because I mean we're still working on that. But this was just a curiosity. Of course, we have done for lambda for these two plots for a specific value of lambda star and n equal to 4. But you can immediately convince yourself that the different fixed point value of lambda star corresponds to a slightly different value of n, right? Because lambda star n is kept fixed. In the plot on the bottom, you also see the dependence on capital N, and you still see that the convexity works. This is true also trivially for delta 2 minus 1. So these functions are pretty much convex, more than I was honestly expecting to see. And we don't know yet why this is the case. Maybe there is some trivial thing behind or something more profound, but it would be nice to understand that. So from the part that, I want to talk about from quantum field theory before going to pandemics, what did I not present? So we worked on charged complex CFTs. And that's a very interesting part, and it's very interesting also for the weak gravity conjecture too, right? Because, for example, in the work of Aaron and Hofer, the claim is that for unitary, non-unitary theories, it shouldn't work, and they have examples there, which actually corresponds to have to go to 4 plus epsilon, so negative epsilon. But I mean, we have an explicit example of complex field theory that are smoothly connected to the non-complex field theories by changing physical parameters in the theory. So it's interesting to study those. And there is the ON cubic duality between 4 and 6 dimensions, and Jamal will light us about that. Finally, interestingly, there is also the UN cross UN, and this also leads to intriguing test for the weak gravity conjecture. I did not present safety at large charge, which was actually the original paper, the original work that got me interested in that, and thanks to Domenico and Susanne, because I mean, I was really curious about that. The interesting part of that paper, I believe, still to date, is that it's a computation at in exactly 4 dimensions in a theory which also features fermions. And I think this has been a little bit underestimated so far, but there are fermions in that theory, and there are actually interesting things to explore there. I also did not present, although I would have loved to, but I mean, there's only so much we can say in a talk. About QCD for near conformal dynamics, the dilaton story. And this is also a theory that only has fermions. So this is the work again with Domenico and Susanne. What I love about that is a theory that is a gauge fermion theory. And we using the effective theory below the conformal window with the dilaton to analyze the deformations of the anomalous dimension. It would be interesting to relate these to complex fixed points. I don't think it's been done so far. All right, if there are no questions about this, I'll be ready to move to the pandemic pact. It was clear. In any case, you have the time to think over if you have some further questions. Right. All right, so this is the little overview of the quantum field theory for trying to solve quantum field theory in different regimes. But let's see, what can we do? How do we use CFTs beyond the realm of particle physics? Of course, it's already been used in many, many other realms, but certainly not in epidemiology. Oh, actually, I take it back. Cardi even worked on that in the 80s. But how can we reorganize epidemiology using CFTs? Now, it should be clear that this is a very sensitive issue, given that we're talking about global pandemic, one of the worst several centuries, and this is only the update of the World Health Organization from May 19, 2021, where they were sure that's related to the pandemics around 3.3 million, but it's much, much, much more than that. And clearly it's important to prevent and understand the spreading of pandemics. Let me just say, this is not an understatement, that before SARS-CoV-2, the information about pandemics, it was basically a joke. The reason of that, there were not enough data for that. The last pandemic was the Spanish flu. Both at the genetics level, which means genomic level, and at the epidemiological level, the informations were extremely scarce. But now we have an immense amount of data, so we can use that. All right, again, let me thank these people, including Domenico, that start actually, playing with us on this stuff. And but now the group is really immense, and there's only a selected part of that. It includes high energy physicists from experiments working on machine learning, computer scientists, and plenty researchers too, working on that, and we have a lot of fun. Phenomenologists, and this is again just a short list of papers that we've been publishing, several Nature scientific reports, and one even the Lancet, and being asked to write a report, physics reports on the field theoretical ABC of epidemic dynamics. And then we actually also moved into write the epidemiological theories of various variants, which is very important, as you can imagine, to tame the new emergence of variants. The very, very last paper, on the other hand, is on using the machine learning and genomic sequencing to demonstrate, and we actually could demonstrate that each pandemic wave was actually driven by different variants. This was actually not known before, among the other things which were not known. All right. So when we talk about curiosity-driven research, why did I start this? Well, because in January 2020, we were told we couldn't travel and to postpone our travel. I was supposed to go to travel in the States. I was supposed to give a talk at MIT, stay here for a few weeks. I had no idea when I could travel again, and what really that didn't mean postpone. Could have been 2 months, 3 months, never. And then, we started playing with that with Michele Della Morte, and we realized that by trying to reparameterize the logistic functions, you will see in a second how did we reparameterize that, that in fact we had to indefinitely postpone our trips. So actually it served our interest. And then we played around with that, and Domenico joined later, and it was a great addition to the team. And we had a lot of fun. So let me just, again, I'm going to be very simple about that, okay? So you have a sigmoid function like that represents the, for example, the total number of infected in Italy. These are real data. And you immediately see that, okay, but if you're a physicist at the very beginning of time, this is a constant. At the very end of the time, for the first wave, this could be approximated by constant. So perhaps you would like to write this in terms of fixed points. All right, let's do that. Okay, so you write a nominal beta functions for that. And you can use the logarithm of the number of infected. In fact, you can also use a number of infected. It's just technically from the beta function point of view, you can consider it as a different scheme. Okay. If you do that, you have only 2 parameters in the game. One that I will show you in a second, the physical interpretation of 2 parameters. But once you have these 2 parameters, of course, it's a very simple first order differential equation. You can integrate it, and you have this logistic function in terms of little a and gamma. And b, which is related to the integration time. When you start this. Very good. Now, let me look at the solution of this. And you immediately see that gamma, that is measuring inverse weeks, okay, in this case. On the right-hand side, you have the beta function, right? The origin of the beta function is the origin of your pandemic. And then different gamma for fixed A tells you how rapid this is going to start. If you ever heard about the flattening of the curve, gamma was taking care of the flattening of the curve. So there's a very simple interpretation of the flattening the curve in terms of this parameter here. If you go to the peak, this is the peak of the pandemic for gamma equal to 1. And if you go to the other fixed point, of course, this goes to the end of the pandemic, to the other fixed point. the interacting fixed point will correspond to the final number of constant infected people in the end. Right, excellent. What is A? Well, e to the A is the area beneath this curve, and it's nothing but the total number of infected people in the end. And this remains constant as you change gamma. So there was all the strategies that were actually used during the first phases of pandemics was to curb gamma. So the time structures were reproduced. So I don't want to convince you, you can test yourself, but we have applied this to virtually every single region in the world. So this is actually the success of this. And we were able to demonstrate that with two parameters, little a and gamma, because B is just the initial time where the pandemic starts, we were able to classify each country with these two parameters. And that was very important for then predicting the future. So how did it go compared to, for example, actual data? So I think it was Simeon before has said, I mean, it's fun to talk with data. I think it was also Gabriel Monday say, I want to discuss with data. These are actually data, okay? And not data. These are actually very, very relevant data because they affect humans very closely. And it works also for the number of deaths. So the same type of parameterization works there too. So these are if you do in epidemiological compartments. Please notice that there is a little deviation here, which I will discuss later. So we were very pleased by this, but we didn't want just to kind of fit the data. We were able to predict as soon as what you can demonstrate. If you get close but not too close to the maximum, then you can easily predict when the maximum happens and how long farther away will the wave subside, provided the social measures remains the same. So this actually was very important for predicting a number of consequences of that. On the right-hand side, these are not just random curves. These are actually the curves for each single country, a sample of countries we studied, normalized per million inhabitants. And you can see that, of course, they are very similar in nature, all of them. What are the advantages of this reinterpretation in terms of fixed points? Well, allows you to have analytic expressions, so you don't need supercomputers to investigate these results. It's symmetry-based. 2 parameters per country is typically enough to understand a single wave dynamics, the gross features. The time structures are extremely well described, and once you're very close to the peak, then it becomes extremely predictive. All right. I'll spare for you how do you model the interaction between different countries that led to the world news of predicting what happened in the fall in 2020. But let me just focus now on deviation. Can you see the deviation from that, which we call Stroning region? For people who work on walking dynamics, this is the equivalent of walking for pandemics. Okay, so something that doesn't really stay still, but it starts growing up again. So now, obviously, the first thing you think as a physicist, okay, this is an approximate time scale invariance, right? You don't really get to the fixed point. So this glitch in pandemics, it was called endemic behavior. Okay? So how do we model that? Mathematically, what you do, you have a complex fixed point. That is the simplest way to think about it. So rather than having alpha times 1 minus alpha, now you have actually another parameter that tells you did not really have to the fixed point, but you have something like that with a certain power p. This is the modulus of the beta function as a function of the real and imaginary part. These are the 2 fixed points, the one you have in green. And you can see that indeed you have a very good representation of this. And also it predicts that there will be another wave later. Because effectively, so this gives 2 time scales in the problem. And this is the presence of the fixed points. So governing the second wave dynamics is actually given by this delta, right? The delta is, if you want, this object here. If delta gets to 0, then you did a great job in killing the pandemic. If the delta was not going to 0, then you did a bad job to do that. This is an absolute number we could measure for each single country in Europe. Again, if you want to see the solutions, again, these are hypergeometric functions, so the closed form solutions. So you can actually solve for that. And then you see again the behavior here, right? So delta equal to 0 would be a perfect ultraviolet fixed point, sorry, infrared fixed point in the theory, large scales. Different delta corresponds to having a pandemic starting again later. How do we compare it with the data? Well, it's not too bad. That actually, this was second and third wave effectively, okay? And now you see that thanks to this approach, which we call the complex ERGO search, you can define a parameter that tells you actually how many new cases, how little new cases you needed to have during pandemics to push away the second wave. So then this was used because it was also found independently by other colleagues to write a Lancet call for how to implement strategies in Europe. And it's amazingly predictive. So many new cases per day you can afford before vaccination to actually not have new waves. All right. So I think I'm basically done. So there are many more things that I'm sparing you from, but you can ask. So what next? I'm still very much interested in understanding the diatonic dynamics, also for, because I've been working on that for very long, for the conformal window, and what can we tell a large charge? How do we go beyond scalars? I know that's not an easy task. But it will be interesting. Very much along the lines of the work by Ofer and I would like to understand better the relation to gravity, because I mean these theories don't really have gravity, so they only have this conformal dimension. Would be nice to understand better what else one can say from both sides, and I look forward to learn more from that. I hope I convinced you that CFTs have the potential to be extremely useful for society beyond what we've been doing so far. And I think it's not been tapped into that potential yet. I'm sure that we have anything we have overlooked, and where you will be of an immense asset with your deep knowledge. The rest of the dots, I'm sure you will fill them in yourself. So, but with that, I'll thank all of you and the organizers for giving the opportunity and for your patience to go through this. Thanks a lot.
Well, thank you very much. Are there questions for Professor Sannino?
I have one question.
Hey, Tor, good to see you.
Hi, good to see you too. What is the first bullet point? Can you explain what is the main problem there that you see?
Well, I mean, as you know, there's been a lot of questions whether or not you have a dilaton to start to hit in near conformal dynamics and all the characteristics there. So we, in the paper with Domenico, we have assumed there was a dilaton and calculated the corrections to the would-be fixed point, anomalous dimensions, as a function of the background, classical background you put there. So the relations here I would like to have is this, right? So we say that delta over delta star, or delta star. So if you have this, right, and we really have this kind of dynamics right here. So this is beta, this is a function of alpha. This will, at this point, you will have delta star, right? And this is 1. Plus some log Q. And then you have some function of the background. At the same time, you know, as you remember, you can also think about that you have complex fixed points, right? And then at this point, you studied CFT at the fixed points, and then your delta now is delta of the complex CFT is a real delta plus I imaginary delta, right? I really would like to see the relation between this, because I mean, they're both interpreting the physics close to that. Here we use the dilettante, okay? Here, you know, first, here for theory with fermions, it's more complicated to actually investigate that. But for theories with scalars, where we know that there are complex fixed points, in principle, you could also investigate this directly. So, for example, this theory of UN cross UN or UN cross UN, where you have in the window, you can go from the fixed point to non-fixed point, but now only in terms of scalars. So you should be able to have both investigations and see how they're related. I don't think it's ever been done. I'm sure it's never been done. So this I would love to understand that. For example.
Thanks.
Thanks for asking.
So I have a question about the pandemic part. I mean, so you presented a very successful phenomenological model for the pandemic, but do you have any understanding of why this model works?
Yeah. Well, I mean, the question is that maybe yes, I did not say it. Yeah. So in epidemiology, so far from 1990, since 1927, the models were used to call SIR models. The SIR stands for susceptible, infected, removed, or recovered. This is a set of first-order differential equations that actually allow you to do that. Now, if you eliminate the R and you only have SI, then you can demonstrate that because S plus I and plus R is a constant. I just need to close it open, just give me. It will work eventually in the end. So, but as this reopens, let me say that the SI model is been demonstrated by Cardi in the 80s that it's actually a mean field of percolation model at the fixed point of the phase transition between the short range phase to the long range phase. So what we're writing is effectively a mean field approximation of the solutions of that model using symmetries. So the SI is if we want a brutal approximation of that, but it's a mean field works. But if you search really for the compartmental solution, a better way of rewriting these effective field theories in terms of symmetries of the problem. So that is the way we think about that. But there is, yeah, so anyway, so the SI plus I is a constant. And you can demonstrate when you do that, indeed, the beta function you get, sorry, the differential equation you get of di at the end, dt, is indeed of the type I1 minus I. So it's such a demonstration that is correct. But as you go beyond that, then effectively it's not that. So then we also studied that the mapping between the generic SIR and the ERG corresponds to an SIR with coefficients which are time dependent. It's very well known that the SIR only works on, extremely short amount of time in terms of predictions, and then becomes basically useless, in fact. But this, on the other hand, being based on the symmetries, with few constants, actually only two, reproduce the entire wave behavior. So it's actually stable over several weeks, so no months. So this we understand the fact that we have captured the final initial symmetries immediately, which is what you would have expected by using symmetries.
Yeah. Okay, thanks.
I don't know if that answered your question.
Yeah, thanks.
Yeah, you're welcome. Yeah.
Well, I think maybe we are at the time limit. So further questions, maybe we can defer till